Hi, my name is Daniel,
I'm Anton.
and this is our autonomous vehicle training using synthetic and real data with conditional deep convolutional GAN. So start off walking with you guys our notebook. We have our imports.
And so in this first block, we're gonna be training our conditional DCGAN. So we decided to go with a latent dimension of 512 and an embedding dimension of 128, as this would allow us, our model, to learn more of the features of the classes. And we chose a smaller image size of 32 by 32 to reduce computational complexity when training the model. We had a learning rate of 1e to the negative 4 and beta 1 and beta 2 of 0.5 and 0.9 for momentum in our atom optimizer. So as you can see, these are parameters. And these are just helper functions to actually generate the images. And in this block, we have our generator and discriminator class for our conditional DCGAN. So our generator uses the NN module from PyTorch, and you can see the architecture here, as well as for the discriminator. And as we keep going, we load the classes as objects, and we're using the atom optimizer. Keep going. So now we're at our actual training loop. So in the training loop, we simply load the models in evaluation mode and we train them. So we go through. So we train the model over 200 epochs. And as you can see, we can show more outputs, but it's basically the same all the way up until 200. And finally, here is our loss graph for our DCGAN. So as you can see, the discriminator loss is around 0.5 to 0.4 range, which is what we expected in terms of like the actual output, as the discriminator should be guessing around like 0.5 if the generator is generating images that are realistic enough according to the loss function.
Cool. So next we have a function that generates a grid of just generates enough size data set for our fake images, and then we basically save that in a folder, the same structure. We basically picked 15 classes from a German street sign data set, and we're trying to challenge our model by picking a lot of similar looking ones. For example, the street signs with the speed limits, a lot of them are they're all the same shape, it's just the different numbers. So, and under also different environments. So we were originally having issues like generating images that had variety in them, and we think that was because of modal collapse in the actual the discriminator was basically memorizing what the real images were, and always picking it, and then that was not helping our generator get any of the gradients that I needed to improve. So we basically added some noise in our training, which I will show you right here. Adding some noise there helped a lot. Basically just a tiny bit of Gaussian noise in between for the real images every time it's looping through, so that the discriminator can't just memorize which ones are real, and then that helped a lot. And basically we saw immediate improvement. All the images are a lot more clear under different environments, and if we look through our data set, some of the pictures are even very shot in nighttime. So we can see that we have the 60 here is pretty dark, but you can still tell it says 60. Same with the 70, so on. The stop signs also were really clear from the get-go. We were originally struggling a lot with the speed limit signs, and we also picked a few different shapes, and different colors too. So yeah, we wanted to compare it with. We just generated another one for 15 random images from all our 15 classes for the real images, and you can tell that just because the image quality is pretty low on the data set, around 32 by 32 to 64 by 64 in that range, they look pretty close. Maybe there's less variation in size, but even so, you can still see some orientation differences, like with the steer, yield sign, and so on.
Yeah. So now we're gonna go over our classifiers. So these we decided to use ResNet. We re-implemented the ResNet 10 module that we used in a previous assignment. The reason we chose ResNet was because of the skip connections, and we also implemented batch normalization. So this would allow the model to really learn like the features of each class better. Again, we're using an atom optimizer. So we use the same learning rate of 1e to the -4. However, for our classifier, we only trained it over 10 epochs because we already saw good results after around 4 or 5 epochs. So this is just the training loop function, as we can see. Again, we have like the back propagation and all that good stuff, and we train it over 10 epochs, and this is the training loss graph. So as you can see, we start at around 1.2 and converge close to 0. So this was for our ResNet model that was trained on a purely synthetic dataset. And here's our ResNet model that was trained purely on real images. So again, it starts off at 1.2 and converges down to around 0. And in our final code block, we test both of the models trained on synthetic and real images, but we train it on one test set that is composed of real images. So as you can see, we have the accuracy per class and the overall accuracy, and both of the ResNet models had 100% accuracy on the test set.
Thanks.
Thank you.